In part C, we once again have a couple components or a couple different ingredients in my overall function that I'm trying to transform. And fortunately, this first one is ready to go. There's no switch. It just starts at t equals 0 and we never turn it off. So that'll be pretty straightforward to transform. The second component is a little trickier. At pi seconds, I'm going to turn on sine of t. In terms of graphing that or understanding that behavior, that's also pretty straightforward. But as we saw in the previous example, before I can apply our theorem to find the Laplace transform of this term, I have to make sure that the shift in the function matches the switch, which in this case turns on at t equals pi seconds. So I need to do something to rewrite and manipulate this sign so that it's actually in terms of t minus pi. So here I've just left myself a little room to just kind of figure out what I need to do so that these two functions are actually equal. In the previous example, we had exponentials, and so I could sort of peel off one of the e's or two of the e's. In this case, and this is true most of the time that I'm dealing with some sort of trig function, I like to just kind of take a step back and think about what's true about this function and this function, and then there's typically some way to make these two align just based on their properties. Here I've graphed y equals sine of t and y equals sine of t minus pi. So again, I have sine of t. I need my function. I need this function to be sine of t. If I just have sine of t minus pi by itself, obviously those two functions are not equal. This has been shifted to the right by pi units. So you can see sine starting here, and then on this blue function, it's the same function, but it starts here, pi seconds, as it were. But again, I need these two to align. I need them to be equal. So in this particular case, it's relatively easy to accomplish that. I just need to take this blue function, which is what I have now, and I need to reflect it across the x-axis. So I accomplish that by multiplying it by -1. So if I were to take this blue function, which is sine of t minus pi, multiplied by -1, that would reflect it across the x-axis or the t-axis, and then that would be equivalent to the function that I'm actually dealing with. So this is an example of the type of modification that you need to do in order to get this function to be shifted by the same amount that our switch corresponds to. And as I mentioned with trig functions, I typically do something like this. There's no real clear-cut strategy. I'll just look at the function that I have, identify the function that I want, and then just think about their properties in order to be able to figure out what I need to do to get them to match up. Now that I've got my g of t written so that this term here has a shift which matches the switch, I can go ahead and take the transform. So this is what I'll get for that transform. Just as a reminder of the structure of this theorem, when I transform sine of t minus pi, I'm actually just going to get the transform of sine of t, because this shift has been accounted for in the theorem and works along with this switch to introduce this exponential function. All right, we have one more example, part D. In part D, we once again have a couple components, and looking at this second component, I kind of prefer this one this time because my switch is at 3, and I can kind of tell that I have already modified this. Well, actually, let me slightly rewrite this first term. Here I've rewritten it up front, so it'll be the first term, and in this exponent, I simply factored out a negative. So now these shift components line up perfectly with my switch, so this term is ready to go. Now for this first term, or these first terms, if I was to distribute this through, this is going to be a little bit more work. So here are the terms that I need. I have a t squared times u sub 1. So in order for the structure to align with what is required by the theorem, I need to make sure that that's shifted by 1 unit. So I need this t squared times u sub 1 to be somehow written in terms of t minus 1 squared times u sub 1. Similarly, I'll need this t squared u sub 2 of t to somehow be shifted so that it's in terms of t minus 2 squared. Clearly, these two things are not equal. T squared does not equal t minus 1 squared, and t squared does not equal t minus 2 squared. So when I write in terms of this structure that I need, I have introduced additional terms. So in this case, what I'm going to do is I'm actually going to kind of FOIL out these quadratics, see which additional terms I've introduced, and then I need to account for those back at the end of my function here. So when I FOIL out this t minus 1 squared, I'm actually getting t squared minus 2t plus 1. What that means is, in my original function, the only term that actually existed was this t squared times u sub 1. So this negative 2t plus 1 times u sub 1 is new terms that I've added in order to be able to have this structure that I need. So I've added negative 2t plus 1. So out here on the end of my function, I'm going to have to subtract that off. And that is, of course, multiplied by u sub 1. Playing the same sort of game with this second factor, I originally had t squared times u sub 2, but now I've introduced negative 4t plus 4. And now I have to be careful here because I am subtracting that negative 4t plus 4. So in order to accommodate for it, I'll need to add that same term times u sub t here at the end of my function. So now my g of t started out looking pretty innocent, and now it's pretty involved. This whole thing here is my g of t. And actually, unfortunately, we're not even done yet, because as I look at these new terms which I've introduced, this term here, for example, is switched on at 1. Therefore, this term has to be shifted so that it's in terms of t minus 1. Similarly, this term, which is turned on at t equals 2, has to be shifted so that it's in terms of t minus 2. Let me go ahead and try to accommodate all of that and finally write my actual g of t here. Okay, so this is a little elaborate here. My first term I've just copied straight down. These second two terms I've also copied straight down, and those have the structure that's required by my theorem. The shift matches the switch. And then these terms, which I originally wrote in orange up here, were added to my function to accommodate these shifts here, and then I needed to shift those appropriately as well. And so I've just done a little reverse engineering. Again, this t needs to be in terms of t minus 1. So if I want to force that to be t minus 1, then in order to balance things out, I needed this to be a positive 1 in here. And you can work backwards and confirm. If I was to distribute all of this, I would get 2t minus 2 plus 1. So this entire quantity is 2t minus 1. And notice that this quantity here, when I distribute the negative through, is also 2t minus 1. I play the same game with this term, and instead of simply writing negative 4t plus 4, I need to write it in this kind of expanded, convoluted version so that the shift will match the switch. I could actually push this a little further algebraically and distribute these switches here and then maybe collect that, but I'm not going to bother. I'm just going to go ahead, and now that I finally have the appropriate structure, I'm going to apply the Laplace transform to this entire expression. Okay, so this is my Laplace transform. Let's just briefly go through kind of term by term. This first term has the structure of t e to the negative t. Of course, it's been shifted, but that's okay. So I'm simply going to take the transform of t e to the negative t. We have a theorem that says if you have the product of two functions and you're taking its transform, well, actually, not just any two functions, but some function times an exponential, and that actually yields a shift in the transform. So this is like the transform of t, but I've evaluated it at s minus negative 1 because of that coefficient there. Of course, I include the exponential term, which accommodates for the switch, and that's my transform of that first bit there. Moving on, I'll take the transform of t squared, which is 1 over s squared, include the appropriate exponential term. This is, once again, the transform of t squared, negative t squared, and then I have a different exponential to accommodate for this switch. And actually, that points out that this numerator is a typo. That should be a 2. Problem solved. And then when I look at, for example, this expression in the parentheses, I'm going to treat that as 2t plus 1. And then I'll multiply by the appropriate exponential to accommodate this switch and the corresponding shift. So if I just transform 2t plus 1, I get this expression here. Similarly, in this set of parentheses, I really want to just think of this as negative 4t minus 4. And so this is the corresponding transform. And then to accommodate this shift and this switch, I introduce this appropriate exponential. So I'll admit that example was pretty involved. But if you think about the steps that we did, it was mostly algebraic steps that were required to restructure my g of t so that it would have the structure required by the theorem. So I wasn't doing any calculus or difficult derivatives. I was simply reworking my function, rewriting it algebraically so that it would have the structure that's necessary. And actually, just for fun, if you want, you could take this g of t here, this entire expression, FOIL everything out, collect like terms, and eventually you should end up with the much simpler g of t that we started with. So if you feel like it, you can try that on your own just to confirm that it actually works out. We have now seen several examples of taking the transform of functions that involve these heaviside step switches. So we, of course, must also practice doing that process in reverse. So in example 4, we have been given transforms. We will reverse the process to identify the original function that these came from. So in part A, I see several transforms that I'm familiar with. I know that 1 over s comes from the constant 1. And then now we're seeing these exponential terms, which indicate that some of these components have been shifted and switched on at a certain point. I expect this first example will be relatively straightforward, and then the examples will increase in difficulty and tedium as we go on. So maybe this first one we can just state the inverse transform straight away. Getting started here, I'll call my inverse transform little f of t, and if I take the inverse transform of 1 over s, that gives me 1, and then if I take the inverse transform of negative 1 over s, that'll also give me 1, and then this exponential indicates that this function has been switched on at 1 second. Moving on to this next term, I recognize 1 over s squared as the transform of t. So its inverse transform will be t. But because this includes this exponential, that means that the inverse of this has been shifted over by 1 unit and multiplied by the appropriate step function. So again, I look at this 1 over s squared, and I recognize that the inverse of that transform is t, but I need to shift that inverse, and so I'll write it as t minus 1, and then I introduce the appropriate heaviside switch as well. Treating these last two terms similarly gives me these inverse transform terms here. Now you may ask, for example, on this last one, since it's switched on at 3 seconds, or the inverse must be switched on at 3 seconds, why didn't I shift the inverse by 3 as well? And the answer is, well, I kind of did. I mean, the inverse in this case is simply a constant, and so if I shift it to the right or to the left, the name of that function won't change. Same is true up here. I didn't need to somehow rewrite this in terms of t minus 1 because this function doesn't have any t's in it. So this will be my inverse transform. Let's go ahead and take a look at part B. This is a relatively simple transform. I kind of don't like the fact that I've got this one fraction here. So maybe as a first step, I'll split it up into 2 separate fractions because I've got that one denominator. And then I prefer this exponential to be sort of pushed off to the side so that I can clearly see what the transform is itself. And so here I've just rewritten it again with that exponential sort of pushed off to the side. I think I can identify the inverse pretty much straight away. Finding the inverse of this, I recognize this as the transform of t, and then I recognize this as the transform of t, but I need to shift that inverse transform by 2 seconds, and then also multiply by the appropriate step function. So this will be my inverse transform. If I just rework that a little bit algebraically, I can write it in a slightly different form that maybe makes the structure of this function f of t a little bit clearer. At t equals 0, I have t, so my function will be increasing linearly, and then at 2 seconds, I turn that off. And at 2 seconds, I simultaneously output a value of 2. So here's a quick sketch of what that function looks like. I have linear growth from t equals 0 to t equals 2. At 2 seconds, I turn off that linear component, and then the function remains at a value of 2 as t values increase. Let's take a look at part C. As expected, these examples are getting more complicated as we go along. I see several switches, and I actually essentially see one function. So before I try to find the inverse transform of this Laplace transform, I'll once again rewrite this in just a slightly different way, where I've pushed all of these exponentials off to the side. And then this has kind of got an interesting structure, because clearly this fraction is a recognizable transform. This is the transform of cosine of t. And then if you look at what's happening, I've got the transform of cosine, and then that's being multiplied by these exponentials. I know that each of these exponentials, when they're multiplied through to this fraction, will require me to shift the corresponding inverse, as well as hit the corresponding inverse with an appropriate Heaviside switch. Now, if I wanted to, I could distribute this fraction through to each of these exponentials and see that structure a little bit more clearly. But I actually sort of feel that this form here is actually pretty clear as it is. What we do sometimes, and this is something that we encounter relatively common, is we'll name this transform component something like capital H. So we recognize that we've got a transform that we know, and we'll call that capital H. And then since that capital H is multiplied by several switches, I know that each of those switches will yield the inverse transform of H, which I've labeled here as little h of t. And then this exponential has a sort of coefficient in the exponent of pi. So I know that that inverse transform must be evaluated at t minus pi. And then I must hit that with a u sub pi of t to turn that function on at the appropriate time. So I'm actually not going to do any more modification with my original capital F here. I just want to kind of use this structure to write out all of the different cosine terms, in this case, that I'll get. So using this sort of notational structure, when I take the inverse transform, each of these terms will yield a cosine of t, and then to accommodate this e to the negative pi t, first I'll take that cosine of t and I'll evaluate it at t minus pi, and then I'll multiply that by u sub pi. To accommodate this second exponential, which is in my transform, I'll take the cosine of t and I'll evaluate that at t minus 3 pi and then multiply by the appropriate switch. Same thing with this last term here. Now I know how to evaluate cosine of t at t minus pi. I just use this notation to sort of emphasize the structure that the inverse transform here will be cosine, but then I'll actually have to implement this shift. So in this case, I won't leave this as my final answer. I'll go ahead and write each of these cosine terms in terms of the appropriate shift. So I'll get a little f of t that looks like this, where each of my cosines is evaluated at the appropriate shifted expression in terms of t. This intermediate step isn't necessary, and once you've kind of seen a few of these examples, if you want to go straight from this structure of the transform to this solution, that's fine. I just write this intermediate step to reiterate the structure of what's going on. So let's finally take a look at our last example. So in this last example, I once again see a couple of switches, and so let me first start by sort of pushing those off to the side. So I have these two switches effectively at t equals 5 seconds and t equals negative 20 seconds. So sort of using the structure that we introduced in the last example, if I call this fraction here capital H of s, then I know that my final solution will have this structure here. I need to find the inverse transform of this, and then that inverse transform will be evaluated at t minus 5 because of this exponential, and then I'll multiply that by the appropriate step function, and then this second exponential will lead me to take that same inverse transform, evaluate it at t minus 20, and then multiply by the appropriate switch. I guess that should say sub 20 there. Or alternatively, I could write it in this structure here. Once I've found my little h, I need to plug in t minus 5, multiply by u sub 5, do the same thing with t minus 20 and u sub 20, and that'll be my final solution. It sounds so simple, but unfortunately, this capital H of s is kind of a beast. First of all, I certainly recognize it as a fraction, but I've got this cubic in the denominator that I'm going to have to manipulate pretty extensively before I can identify exactly what the inverse transform of this fraction is. Let me go ahead and isolate this capital H and just work on it for a little bit, and then I can theoretically put its inverse transform back into the structure here to build my final solution. First, I notice there's an s that I can factor out of each term in my denominator. And now looking at this quadratic, I would love to be able to factor that, but I don't think it'll work. And so the next thing I need to do is use partial fraction decomposition to split up this overall fraction. I haven't worked through the steps here, but you can confirm that if we implement partial fraction decomposition, I'll get these two fractions here. This first fraction is ready to go. I know that that is the transform of just 1/2. This second fraction, unfortunately, is not. My denominator does not factor, and so what I'll need to do is I'll need to complete the square on the denominator, which puts my denominator in this form. I actually notice a typo. This 2 here got dropped, and so that 2 should be inside on that quadratic term, and then there should be a 2 here. And the first step in completing the square would be to factor that 2 out. So that's why I have this 2 outside of the denominator. That would leave me s squared plus 1/2 s plus 1. And if you remember, when we complete the square, we add half of that linear coefficient, and then I have to accommodate that. Again, I've skipped the steps here, but hopefully you can confirm that this is what I'll get in my denominator. And now in my numerator, this is shaping up to be something like, s squared plus a constant squared. And my numerator has an s in it. Therefore, I need those to match. So I actually need to force this numerator to have an s plus 1/4. And in order to accommodate that, I need to take this 1/2, in a sense, break it into this 1/4 and then another 1/4. So as I said, this one's a little involved here. But having done all of that algebra, this term here, again, can clearly be untransformed. And now it's not obvious, but this term can be untransformed as well. I'll actually need to split this up into 2 separate fractions so that I have this s plus 1/4 over this denominator along with this 1/4 over this denominator. And if this denominator was simply s squared plus 15/16, I recognize that as being sine or cosine. Of course, I'll need to take the square root of this, and since it is instead s plus 1/4 squared, I recognize that I have multiplied my inverse transform by e to the negative 1/4 t. Anyways, like I said, let me go ahead and write out my little h of t and then kind of talk through term by term. So in all of its glory, there's my little h of t. Again, I would encourage you to take some time to work through those details and confirm that this is the inverse transform of this expression here. For now, I'm going to leave it at that. And then we also recognize that this isn't even my final solution. Remember, this is just the inverse transform of this fraction. Because that fraction is multiplied by these exponentials, we know that our final solution, f of t, would be this function here, where this h of t is plugged in and evaluated at these appropriately shifted expressions. I think I lack the moral fortitude to actually write out that full solution. So what I'm going to do is just sort of reference these two components and just indicate that I have technically built my full solution, my full inverse transform, little f of t, and I could theoretically put it all together, but for purposes of this lecture, I'm just going to leave it as it is. So in this section, we have discussed discontinuous functions pretty extensively. We've introduced this Heaviside step function as a tool for representing discontinuous functions in a pretty efficient way. And then we've seen a few examples of taking the transform and finding the inverse transform of functions that involve such discontinuities.